Welcome to a deep dive. Today, we're digging into something pretty fundamental to, well, everything digital, really. How software gets tested.
That's right. And we've got some great source material here, excerpts from O4 Test Analysis and Design. It's part of the syllabus for the Certified Tester Foundation level.
So this isn't just theory, it's the practical stuff.
Yeah.
It lays out these systematic ways testers figure out, what actually needs testing and then how to design good tests.
Exactly. It's about being methodical.
And our mission today, really, is to unpack these different approaches for you. Give you a shortcut, maybe, to understanding the craft behind making sure software, works, so you can appreciate what goes into the apps and systems we all rely on. Okay, let's get into it.
Absolutely. And the material breaks it down nicely. We've got three main types of techniques. Black box, which is based on specifications.
Looking from the outside in.
Right. Then white box, based on the internal structure, the code itself.
Looking under the hood.
Yeah. And then experience-based techniques, which leverage the tester's own knowledge. Plus, we'll touch on some collaboration approaches too, which are more about preventing issues up front.
Okay, let's start right at the beginning then. Why do we even need these systematic techniques? Why not just, click around to see what breaks?
That's a great question. Clicking around, sometimes called ad hoc testing, definitely has its place, but it's usually not enough. Systematic techniques are crucial. They give testers a structured way to approach, first, the analysis figuring out what to test.
Okay.
And second, the design figuring out how to construct those tests effectively.
So it's about discipline, guiding the process.
Precisely. It helps you move beyond just random poking. You develop a set of test cases that's relatively small, manageable, but still gives you good coverage and confidence. Think about modern software, it's incredibly complex. You simply can't test every single possibility.
No way.
So these techniques help you select tests systematically.
And they help you nail down the specifics too.
Yeah.
Like what data to use.
Yes, exactly. They guide you in defining the specific test conditions, what situations you need to check. They help identify the coverage items like which requirements or code paths or data ranges you need to hit. And like you said, they help identify the test data needed to actually execute those tests.
Got it. And the main buckets, again, were black box, white box, and experience-based.
That's the classification from the syllabus, yeah.
Right. Let's dive into that first one then. Black box test techniques. You said it's like looking from the outside.
Spot on. Black box, or specification-based techniques, treat the software like an impenetrable box. You focus only on what it's supposed to do based on its requirements or specifications, its external behavior. You deliberately ignore the internal code or structure.
So the tests you design, they shouldn't care how it's built inside.
That's the idea. If the developers completely refactor the code, change the algorithms, whatever, as long as the software still follows the same external rules, your black box tests should ideally still pass. You're testing the what, not the how.
Okay, first specific technique here. Equivalence partitioning, EP. What's the gist of that?
EP is really useful when you're dealing with inputs or maybe even outputs that can have a huge range of possible values. The core idea is you divide all possible data into groups or partitions.
The groups.
Yeah, partitions. The key is that you expect the software to handle every value within a single partition in exactly the same way.
So it's like a shortcut. If one value works, they should all work.
Pretty much. That's the theory. If testing one value from a partition finds a defect, then testing any other value from that same partition should, in theory, find the same defect. So you only need to test one representative value from each partition.
That sounds way more efficient than trying every number.
Oh, absolutely. It's a huge efficiency game. So you define these partitions. They shouldn't overlap, right? Each value belongs in only one, and each partition needs at least one value. And crucially, you identify both valid partitions, things the system should accept, and invalid partitions, things it should reject or handle as errors.
Okay, valid and invalid groups, and the goal is to test one from each.
Exactly. The coverage item, as the syllabus calls it, is the partition itself. Achieving 100% coverage here means you've designed tests that exercise at least one value from every single partition you identified. If you have multiple sets of partitions, like for different input fields, the basic approach is each choice coverage test, one from each partition in each set.
Makes sense for handling big data ranges. But what about the edges? The transition points between these groups?
Excellent point. That leads us directly to the next technique, boundary value analysis, or BVA. BVA builds right on top of EP, but it's specifically for partitions that have some kind of order, think numbers, dates, times.
Okay.
The core idea of BVA is to specifically test the values at and around the boundaries of those equivalence partitions.
Why focus so much on the boundaries?
Well, experience and statistics show that's where developers often make mistakes. Think about conditions like less than or equal to, greater than equal to. It's really easy to get those slightly wrong and off by one error using CNM instead of things.
Yeah, I could see that, those edge cases. And the syllabus mentions two flavors, 2-value and 3-value BVA.
It does. So 2-value BVA is the simpler one. For each boundary, you test the value right on the boundary and its single closest neighbor in the adjacent partition. So if a valid range is 1 to 10, you'd test 1 the boundary and 0 its invalid neighbor below. And you'd test 10 the other boundary and 11 its invalid neighbor above.
Okay, so just the edge and one step over. What about 3-value?
3-value is more thorough. For each boundary, you test the boundary value itself plus its immediate neighbor on both sides. So for our 1 to 10 range, around the lower boundary, you'd test 0, 1, and 2.
Got it, inside and outside.
Exactly. And around the upper boundary, you test 9, 10, and 11.
That feels like it would definitely catch more subtle errors.
It absolutely can. The source material gives a classic example. Imagine the requirement is if x equals 10, but the programmer accidentally writes if x equals 10.
Okay, common mistake.
Now, if you use 2-value BVA, you test 10 and 11. Well, 10 equals 10 is true, and 11 equals 10 is false. That actually matches the outcome you'd expect from the correct equals 10 logic for those specific values, so the bug might slip through.
Sneaky.
But if you use 3-value BVA, you also test Michael's 9. With the wrong code, if x equals 10, 9 fails the check. It's false. But with the correct requirement, if x equals 10, 9 passes the check. It's true. So the test case using equals 9 would fail, and boom, you found the boundary error.
That's a brilliant illustration.
Right.
Really shows why testing both sides is key. So for BVA, the things you need to cover, the coverage items, are those boundary values themselves and maybe their neighbors, depending on 2-value or 3-value.
Exactly right.
Okay, next black box technique is decision table testing. This sounds like it's for more complicated situations with lots of if this, then that kind of logic.
You nailed it. Decision tables are perfect for testing systems driven by complex business rules, where the final action or outcome depends on a specific combination of different conditions being true or false. They give you a really systematic way to map out and test all that logic.
How do you actually build one? What does it look like?
It's structured like a table. You list all the relevant conditions in rows at the top and all the possible actions or outcomes in rows at the bottom. Then the columns represent the decision rules. Each column shows a unique combination of condition outcomes, like true-false for each condition, and then indicates which actions should happen for that specific combination.
So you're basically mapping out every possible scenario of inputs and seeing what should happen.
Pretty much, yeah. You identify all the conditions that matter. Maybe it's, is the user logged in? Is the item in stock? Is the discount code valid? Then you figure out all the possible combinations, yes, no, yes, noise, and so on. For each combination, you specify the expected result, allow purchase, show error message, apply discount. You often use notations like T and F for true-false, maybe a dash bracket if a condition doesn't actually matter for a particular rule, and then an X to mark which actions should occur.
What's the big advantage of doing this? Seems like a bit of work.
The biggest win is that it forces you to think through all the combinations systematically. It's incredibly powerful for catching overlooked scenarios. And here's a key thing. It often reveals gaps or even contradictions in the requirements themselves before you even test the code. You might find combinations of conditions that the business rules didn't specify what to do with.
Finding flaws in the rules, not just the implementation. That's huge. Any downsides?
The main one is complexity, or scalability. The number of columns, the decision rules, grows exponentially as you add more conditions. If you have, say, 5 conditions, that's 2 to the power of 5, which is 32 combinations. Add a few more conditions, and the table can get enormous really quickly.
Right, could get unwieldy.
Exactly. So testers often have to use techniques to simplify or minimize the table, perhaps collapsing rules where some conditions don't matter, or focusing only on the combinations considered highest risk.
Okay, makes sense. Last black box technique on the list. State transition testing. This sounds like it's for systems that change behavior based on what happened before, like steps in a process.
Precisely. It's designed for systems that have distinct states and move between these states based on specific events or inputs. Think about logging into a website. You might be in a logged out state, then an entering credentials state, then a logged in state, maybe an account lock state, or even a simple traffic light.
Okay, so you map out these states and the paths between them.
Exactly. You model the system's behavior, showing the possible states it can be in, and the valid transitions, the events that cause it to move from one state to another. You can draw this as a state diagram, which is visual, or use a state table.
A table, how does that work?
A state table lists all the states down the side and all the possible events across the top. Then, in the cells where they intersect, you show what the next state is and what action, if any, occurs. The really useful thing about state tables is they make it easy to explicitly show invalid transitions to events that shouldn't cause a state change from a particular state.
I see. And testing involves triggering these transitions.
Right. A test case usually involves a sequence of events designed to walk the system through a particular path of states and transitions, checking that the expected state changes happen and the right actions occur. A single test case can often cover several transitions in a sequence.
And what are you aiming to cover here? Just visit every state.
Well, the syllabus mentions a few levels of coverage, kind of increasing in rigor. The most basic is all states coverage, just making sure your tests cause the system to enter every identified state at least once.
Seems minimal.
It is. A more common and useful level is valid transitions coverage, also called zero switch coverage. This aims to exercise every valid transition shown in your diagram or table at least once, making sure every allowed path between states works.
Is there an even higher level?
Yes, all transitions coverage. This is the most rigorous. It means you test all the valid transitions and you specifically try to trigger all the invalid transitions you identified.
Why test the invalid ones?
To make sure the system handles them correctly. You want to ensure it doesn't crash, get stuck, or end up in some weird, undefined state when something unexpected happens. This is particularly important for safety-critical or mission-critical systems. Oh, and one tip. Usually you test only one invalid transition per test case. If you try multiple invalid things at once, one failure might hide another.
Right, isolate the fault. Got it. So the rigor goes states, valid transitions, all transitions.
Exactly.
Okay, that wraps up the black box world, focusing on the outside. Now, let's flip the coin and look at white box test techniques. This is where we do look inside the code, right?
Correct. White box techniques, also called structure-based or sometimes code-based, rely on analyzing the internal structure and the actual logic of the software. To use these effectively, you need access to the source code or at least detailed design documents. The test cases are designed specifically based on that internal structure.
And the syllabus focuses on two main code-level techniques: statement testing and branch testing. Let's start with statement testing. What's the goal there?
Statement testing is pretty straightforward conceptually. The goal is to design and run tests that execute every single executable statement in the code at least once.
Every line of code gets run.
Basically, yes.
Yeah.
You measure coverage as the percentage of executable statements that your tests actually hit compared to the total number. So you aim for a certain percentage, often 100%.
Okay, hitting every line sounds pretty thorough. Is 100% statement coverage enough?
That's the key question. And the source material is very clear. No, 100% statement coverage is not usually sufficient by itself.
Why not?
Well, think about it. You could have a line of code like result a case Y. Your test might execute that line, contributing to statement coverage. But if your test only ever uses Y2, you haven't tested the case where Y is 0, which would cause a division by 0 error. Statement coverage doesn't guarantee you've tested crucial data-dependent conditions.
Okay.
And it also doesn't guarantee you've tested all the possible outcomes of decision points, like if statements. You might execute the statement inside the if block, but never execute the else block, or vice versa.
Right, so it doesn't cover all the logic paths. That leads us to branch testing then.
Exactly. Branch testing specifically targets those decision points in the code, the places where the execution flow can split. Think of if-then-else structures, switch or case statements, loops, for. A branch is essentially a transfer of control from one point to another based on some condition.
So you're testing the forks in the road.
That's a great way to put it. The aim of branch testing is to exercise every possible outcome of every decision point. For a simple if statement, you need at least one test that makes the condition true, so you take the then branch, and at least one test that makes the condition false, so you take the else branch, or skip the then block if there's no else.
Okay, so you ensure both yes and no paths are taken for every decision.
Precisely. Branch coverage is measured as the percentage of branches executed by your tests compared to the total number of branches in the code. 100% branch coverage means every single possible decision outcome has been triggered at least once.
Now, the million-dollar question, is 100% branch coverage sufficient?
Still, generally no. It's definitely stronger than statement coverage. But even hitting every branch might not uncover defects that only appear when you execute a specific sequence of branches, a particular path through the code involving multiple decisions.
Okay, so neither's a magic bullet. But you mentioned earlier there's an interesting relationship between them.
Yes. This is a really important concept the source highlights. Branch coverage subsumes statement coverage.
So subsumes, meaning?
It means that any set of test cases that achieves 100% branch coverage will automatically, by definition, also achieve 100% statement coverage. Think about it. To test both the true and false outcomes of an if statement, you have to execute the statements leading up to the if, the condition itself, and the statements within the true block, and the statements within the false block, or whatever comes after. You simply can't cover all the branches without executing all the statements on those branches.
Right, but the reverse isn't true. You could hit all statements without hitting all branches.
Exactly. You could have an if statement where your test data always makes the condition true. You'd execute the statements in the then block, hitting those lines, contributing to statement coverage, but you'd never execute the else branch. So you could have 100% statement coverage, but maybe only 50% branch coverage in that simple case.
That's a crucial difference. So branch coverage is definitely the stronger metric. What's the overall value proposition of white box testing then? What's its main strength?
The fundamental strength is that it directly examines and tests the code as it was actually written. This is incredibly valuable because it can find bugs that exist in the implementation, even if the original requirements specification was maybe a bit vague or incomplete or even outdated. You're testing the reality of the code.
But that strength also points to its weakness, doesn't it? If the requirements were incomplete.
It does. The corresponding weakness is that white box testing is generally not good at finding defects of omission, meaning things that should have been in the software according to the requirements, but were simply never coded in the first place.
Because there's no code structure to test if the code doesn't exist.
Exactly. You can't structurally test something that isn't there. Also, white box isn't just about running code. The thinking can be applied during static analysis, like code reviews or walkthroughs of pseudocode. And a big benefit is the objective measurement. Those coverage percentages give you concrete data on how much of the code structure has been exercised, highlighting areas needing more attention.
So if your report shows only 60% branch coverage, you know exactly where you need to focus more testing effort using these techniques.
Precisely. It helps you build confidence based on evidence from the code structure itself.
Okay, let's shift gears to the third main category, experience-based test techniques. This sounds, well, less about rigid rules and more about the tester's own brainpower.
That's a good way to put it. These techniques are all about effectively leveraging the tester's knowledge, intuition, and past experience. They're often used to complement black box and white box approaches, and they can be really good at finding defects that the more systematic methods might miss. The effectiveness, though, really hinges on the skills and experience of the tester involved.
Makes sense. First one here is error guessing. Sounds a bit like fortune-telling.
Not quite fortune-telling, but it is about anticipating likely problems. The core idea is to use your knowledge to predict where errors, defects, and failures are most likely to occur in the software.
What kind of knowledge helps with that?
All sorts. How the specific application has behaved in the past, common mistakes that this particular development team tends to make, typical failures seen in similar types of software or technologies, general knowledge about common programming errors.
So you're using patterns from the past to guess where future bugs might be hiding.
Essentially, yes. A tester might think, I've seen lots of problems with date calculations around leap years, or handling file uploads seems to be tricky for this team, and then they design specific tests to target those suspected weak spots. The source mentions fault attacks as a structured way to do this, basically creating or using a list of potential faults or vulnerabilities and designing tests to try and trigger them.
Like having a mental checklist of things that often go wrong.
Kind of, yeah. A targeted checklist based on risk and experience.
Okay. Next is exploratory testing. This one sounds more like, exploring.
It is definitely more dynamic. With exploratory testing, the tester is doing several things at once. They're learning about the software, designing tests on the fly, executing those tests, and evaluating the results, all in parallel. It's about deep investigation, letting your findings guide your next actions, often going into areas not explicitly covered by pre-written test scripts.
So it's less about having a detailed plan up front.
Much less. It's not about writing out step-by-step instructions beforehand. It can be structured, though. A common approach is session-based testing, where you set a specific time limit, like 90 minutes, define a clear mission or charter for that session, e.g. explore user profile settings and security implications, test within that scope, and then have a debrief afterwards to discuss findings and plan next steps.
When would you find this approach most useful?
It's really valuable when the requirements documentation is poor or missing, or when you're under tight time pressure and need to find high-impact bugs quickly. It's also great as a supplementary activity to formal testing, to catch things the scripts might miss. But again, it heavily relies on the tester's skills, their curiosity, analytical thinking, creativity. A good exploratory tester might even weave in other techniques spontaneously, like trying boundary values they discover.
Sort of improvising based on what they find.
Yeah.
Okay, the last experience-based technique, checklist-based testing. This sounds more structured again.
It is. It's quite straightforward. You use a predefined checklist to guide your testing. You design, implement, and execute tests based on the items on that list.
Where do these checklists typically come from?
They're usually built from experience, knowledge of what's important to the users, understanding common failure points in this type of system, or key quality characteristics. A good checklist item should be specific and verifiable, something you can directly check. They're often phrased as questions or prompts related to requirements, UI standards, or specific functions.
Are there things you shouldn't put on a checklist like this?
Yeah, the source advises against things that can be easily automated. Let the tools handle those. Also, avoid items that are too vague or general. Is the system user-friendly? As they're hard to check consistently. And try not to mix test execution checks with things that are really entry or exit criteria for a testing phase.
And should these checklists be set in stone once created?
Definitely not. That's a key point. Checklists need to evolve. Some items might become less relevant over time. Maybe the team gets better at certain things. You should regularly review them, remove ineffective items, and crucially, add new items based on defects found recently, either in testing or, importantly, in production. The trick is to keep them relevant and sharp without letting them become bloated and unmanageable.
Right, so they provide a useful guide, consistency, maybe especially if you don't have super detailed test cases, but they need maintenance to stay effective.
That sums it up well.
Okay, we've covered looking from the outside, black box, inside white box, and using tester smarts, experience-based. Now, the final category mentioned is a bit different. Collaboration-based test approaches. This sounds like it's about teamwork, not just finding bugs after the fact.
That's exactly the shift in focus. While the techniques we've discussed so far are primarily about detecting defects that are already present, these collaboration-based approaches put a strong emphasis on communication and teamwork to prevent defects from being introduced in the first place.
Interesting. First one is collaborative user story writing. We hear user story thrown around a lot in Agile development. What's the core concept here?
A user story is typically a short description of a feature or piece of functionality told from the perspective of the person who desires it, usually a user or customer. It focuses on the value they get. The source mentions the 3 C's, which is a popular way to think about them. The card, the physical or digital medium it's written on. The conversation, the ongoing discussion to clarify details. And the confirmation, the acceptance criteria that define done.
And there's that common format too, right?
Right. As a type of user, I want some goal action so that I get some benefit value. And then critically, it's followed by those confirmation points, the acceptance criteria.
So how does the collaborative part prevent defects?
By getting everyone involved, business folks, developers, testers, in the conversation about the story before any code is written. Using techniques like brainstorming or just talking it through helps create a shared understanding. Different perspectives catch ambiguities or potential problems early. If the team, including the tester, struggles to define how they would confirm the story works, the acceptance criteria, it's a big red flag that the story itself isn't clear enough or maybe not valuable enough yet. Finding those issues in conversation is way cheaper than finding them in code.
That makes perfect sense and leads right into the next point. Acceptance criteria, which you mentioned, are part of the confirmation.
Exactly. Acceptance criteria, AC, are the specific, agreed-upon conditions that the implementation of a user story must meet for the stakeholders, usually the product owner or customer, to say, yes, this is done and it does what we agreed. From a testing viewpoint, they are gold. They essentially define your test conditions at the acceptance level. They come directly out of that collaborative conversation.
What's their main job?
They do several things. They nail down the scope of the story, what's in, what's out. They help the whole team agree on the expected behavior. They should describe both the happy path, positive scenarios, and important negative scenarios or error conditions. They become the direct basis for acceptance test-driven development tests, which we'll get to. And they also help with estimating the work involved.
And you can write them in different ways.
Yes. Two common styles mentioned are scenario-oriented, often using that given when then format you see in behavior-driven development, BDD.
Right. Given some context, when an action happens, then expect some outcome.
Exactly. Or they can be rule-oriented, maybe just a bulleted list of rules the feature must follow, like password must be at least 8 characters, error message must be shown if username is taken. The key, regardless of format, is that they must be clear, unambiguous, and testable.
Okay, and that brings us to the final collaborative approach. Acceptance Test-Driven Development, or ATDD. You said the AC formed the basis for this. Test first again?
It is very much a test-first approach, yes. In ATDD, the team collaborates to define and create the acceptance test cases before the developers start implementing the user story. This is often done in a dedicated meeting or workshop with people representing the customer business view, the development view, and the testing view.
So you write the tests before the code exists to pass them.
That's the core idea. The team discusses the story and its acceptance criteria, clarifies everything, and then together they define specific, concrete test cases that will demonstrate whether those criteria have been met. These tests act as living examples of how the software should behave. They become the target for the developers.
Can you use the other testing techniques, like black box or white box, when you're creating these ATDD tests?
Oh, absolutely. When the team is deciding which specific test to write based on the acceptance criteria, they can certainly apply techniques like equivalence partitioning or boundary value analysis to select good test data. They might use experience-based thinking, error guessing, to come up with important negative tests. White box thinking might even inform how they structure some tests if they have insights into the underlying system design.
What's a typical order for creating these acceptance tests?
Usually, you'd start by defining tests for the main success scenario, the happy path, then maybe cover alternative success scenarios. After that, you focus on the negative tests, what happens with invalid inputs, error conditions, etc. And if non-functional requirements like performance or security are part of the acceptance criteria, you define tests for those too.
And these tests need to be understandable by everyone, not just the testers.
Hugely important. Since they represent the shared understanding of the requirement, they need to be written in a way that business stakeholders can read and agree with. They should cover the key characteristics defined in the AC for that story, but generally shouldn't test things outside its scope. And you try to avoid redundant tests checking the same characteristic multiple times.
And if you could automate these ATDD tests.
That's where it gets incredibly powerful. When these acceptance tests are automated, they become, in effect, executable specifications or living documentation. You can run them continuously, maybe as part of your build process, to get constant objective feedback on whether the system still meets the agreed-upon requirements as changes are made. It provides a safety net and builds confidence incredibly quickly.
Wow. Okay, that really paints a picture of all the different layers and approaches. We've gone from looking at the spec to the code to using experience and now collaborating to prevent issues. So let's bring back. What does all this mean for you, the listener, tuning in?
Well, I think even if you're not directly involved in testing software, understanding these techniques gives you a real appreciation for the complexity and the professionalism that goes into building reliable systems. It's definitely not just about writing code and hoping for the best.
Yeah, it can help you ask better questions, maybe, about the software you use every day. You can understand that the features you depend on have likely been looked at from many different angles, using specific methodical approaches like these.
Right. It highlights that ensuring quality isn't just one single activity, but it's this continuous effort using different perspectives, focusing on the behavior, the internal structure, likely failure points based on experience, and even making sure everyone agrees on what done means right from the start. Each technique we talked about has its own strengths, its own focus, and helps uncover different kinds of potential problems.
We've covered quite a bit. Systematic black box methods like equivalence partitioning and boundary value analysis for inputs, decision tables for complex rules, state transition testing for behavior over time.
Then we looked inside with white box techniques. focusing on statement and branch coverage to see how much of the code structure we've exercised.
And we explored how tester experience is vital for things like error guessing, dynamic exploratory testing, and using focus checklists.
And finally, how collaboration through user stories, clear acceptance criteria, and acceptance test-driven development helps build quality in from the very beginning, preventing defects rather than just finding them later.
It really shows there's a whole toolkit, a whole range of systematic ways to tackle the challenge of software quality.
Definitely. It's a deep field.
And that leads us nicely into a final thought for you to maybe chew on after this. Given that all these different testing techniques are designed to find different types of defects, and, as we've heard, no single technique is perfect or guarantees finding everything, what does that really tell us about the fundamental difficulty of ever proving software is completely correct? How do we actually build confidence in these complex systems when we know we can never truly test every single possible state or input?